Okay, so just now we have a nice discussion on basically our Lagrangian field theory, and let me again somewhat revise what we have discussed. So, what we started with the writing down of the action integral, right? Which is basically the time integral of the Lagrangian. Now, in a local field theory, the Lagrangian can be written as the spatial integral of a Lagrangian density, which is denoted by curly L, right? Which is a function of one or more fields. Now, we already have a very detailed discussion on the fields where Partho asked me a lot of questions. And also, you see, this curly L or the Lagrangian density is a function of, note this, one or more fields phi and also their derivatives. So we can write it like that. So phi I, which means one or more fields. Now then we invoke the principle of least action, which states that when a system evolves from one given configuration to another between times t1 and t2, it does so along the path in configuration space for which S is an extremum. Now, this is normally a minimum. Now, so we write this condition as this over here, and as a result of which we get down the field equations. Here you will see, as a result of this, we will arrive at our Euler-Lagrange equation of motion of the field. Now, if there are one or more fields than one, then we will have each such equation for the field, for each of the fields. Okay, fine. So this is what we have discussed till now. I think this is quite clear to all of you. So this is how we deal or we start with the quantum field theory, where we have to remember certain very important points. The first is that you see the dynamical degrees of freedom here.
স্যার আমার স্ক্রিন শেয়ারিংটা বন্ধ হয়ে গেছে স্যার।
হ্যাঁ ঠিক আছে, আমি এমনি ডিসকাশন করছি তোমাদের সাথে।
ও
You
ঠিক
have
আছে।
to, yes, yeah, you have to remember that in this quantum field theory, the dynamical degrees of freedom are operators which are functions of space and time, and they satisfy appropriate commutation relations. Another very important feature is that the interaction of fields are essentially local. So the equations of motion and the corresponding commutation relations in space-time depend only on the behavior of the fields and their derivatives at the point of consideration. একটা খুব ইন্টারেস্টিং জিনিস হচ্ছে যে the relativistic and non-relativistic systems, they can be quantized in the Schrödinger, Heisenberg, and interaction pictures. However, in the quantum field theory, Heisenberg picture is used since it is easier to perform quantization in this picture. This is a very important uh, point to remember. Now, I'm not going to show you these things. I'm just going to talk to you about these ideas or so. So, again, if someone asks you that why do we need quantum field theory and what was the basic idea behind of it, again let me recapitulate. We have to remember that in this topic, in regards to this topic of quantum field theory, what do we wish to do? Well, our aim is to develop methods to include fields and the interaction between particles and field into our quantum mechanical description of the world. We want to have a complete quantum mechanical description of the world where we should be able to talk about the interaction between particle and antiparticle. We should be able to talk about mathematically, clearly about the vacuum fluctuations and all that. The first step along this route is to realize that all classical fields are very similar. Their dynamics are governed by linear equations that are that are eventually reduced to simple wave equations describing the field configurations. As a consequence, most fields can be equivalent. It can be equivalently, you see, it can be described as large sets of, or you can say infinite sets of oscillator modes. What does this mean? This means that we can rewrite the Hamiltonian for most fields in such a way that it looks identical to the Hamiltonian for a generic mechanical oscillator or a set of such oscillators. Afterwards, we quantize the mechanical oscillator, and in a way we get the quantization of all classical fields for free. So what is the new idea? The new idea behind quantization of a classical field is to associate the oscillator, which is a classical field, with a level for bosonic particles representing the quantized excitation of the oscillator. Now you have already learnt about first quantization and second quantization. I think all of you know this. Now, what is first quantization? Basically, in first quantization, we have a mathematical prescription which shows that particles behave like waves. As an example, you see the electrons and neutrons are not simply rigid bits of matter, but also they obey wave equations, the Schrodinger equation. Now, this we obtained as a result of first quantization. Okay, just a second. Okay. Now, what happens for the case of second quantization? Now, this second quantization, it gives us a mathematical prescription which shows inverse. That means it shows that waves behave like particles. As an example, you see the electromagnetic and lattice waves are not simply periodic undulation of some medium, but they could actually behave like particles. These phenomena were given particle-like names, photons and phonons. So this is what I'm basically giving you a sort of similarity as well as comparison between the first and second quantization. So you see the basic idea of second quantization.
ফার্স্ট কোয়ান্টাইজেশনে পার্টিকেলকে ওয়েভ হিসাবে ট্রিট করা আছে, মানে কোয়ান্টাইজেশন বলতে কি বলছেন স্যার? সেকেন্ড কোয়ান্টাইজেশনটা বুঝতে পারলাম, ওয়েভের এক্সাইটেশন বা ওয়েভ নেচারকে পার্টিকেল হিসাবে ট্রিট করা আছে, ওয়েভকে আমরা কোয়ান্টাইজ করলাম। কিন্তু
Yes.
ফার্স্ট কোয়ান্টাইজেশনে
ম্যাথমেটিক্যাল ট্রিটমেন্টের
ম্যাটারকে যখন
জিনিসটা আমি ডিসকাসটা করছি। ওইখানে ছিল পার্টিকলস বিহেভ লাইক ওয়েভস। দিস ওয়াজ ফার্স্ট কোয়ান্টাইজেশন।
ডিপ ব্রগলি হাইপোথিসিস এটাই, মানে যে পার্টিকেল ওয়েভ হিসাবে ট্রিট করা যাচ্ছে। এই এখানে কোয়ান্টাইজেশন বলতে কি বলছেন? ফার্স্ট কোয়ান্টাইজেশন মানে
কোয়ান্টাইজেশনটা কোন জায়গায় আসছিল? যখন আমরা ওই যে হারমোনিক অসিলেটর এন্ড অল দ্যাট উইদাউট কোয়ান্টাইজেশন আমরা কোয়ান্টাম মেকানিক্সে তো তাহলে তো ক্লাসিক্যালের মতোই হয়ে যেত। কোয়ান্টাইজেশন মানে ডিসক্রিটনেসটা এসে গেছিল। দ্যাট ওয়াজ দ্য ফার্স্ট কোয়ান্টাইজেশন। সেকেন্ড কোয়ান্টাইজেশন এই যে এখন আমরা করছি কোয়ান্টাম ফিল্ড থিওরিতে, যখন আমরা ওয়েভস, এই যে ফিল্ড থিওরি যখন ইন্ট্রোডিউস করলাম, তখন আমরা দেখাতে পাচ্ছি যে ওয়েভস বিহেভ লাইক পার্টিকলস, এক্সাইটেশন। Particles are basically excitations of a field like this. Okay.
ঠিক আছে, ঠিক আছে।
Now you see the basic idea. I'll be talking mostly about the second quantization. You see, because in our quantum field theory, we are supposed to talk about it. Okay. Now, the basic idea behind the second quantization is that here we start with an expansion of a scalar or vector field. This you have done probably in your quantum field theory class. So what you did was that we started with an expansion of a scalar or vector field in a basis. What does this basis consist of? This basis consists of a complete set of functions. Now, these expansion functions depend on the coordinates of a single particle, and the coefficients multiplying the basis functions are interpreted as operators, and anti-commutation relation between these new operators are imposed. What I am telling you right now is that I am giving you a summary of whatever mathematics you have done in your field theory class. Now, these commutation relations for bosons and anti-commutation relations for fermions, this is what we get as a result of the restrictions. Okay. Now, by doing this, the expansion field is converted into a fermion or bosonic operator field. The expansion coefficients, now you see, have been promoted from ordinary numbers to operators. So this is what second quantization does. And now we have creation and annihilation operators. A creation operator creates a particle in the corresponding basis function, and similarly an annihilation operator annihilates the particle in this function. Now, naturally, a very interesting and important question can come to your mind. And what is that? You can ask yourself, okay, so we have talked about first quantization, we have talked about second quantization. Now, why do we stop? Why is there no third quantization? Right? This can come to your mind. Well, you see, during first quantization, which correspond to particle theories, we are dealing and describing systems with finite degrees of freedom. Now, a field corresponds to description of a system in terms of infinite degrees of freedom, and second quantization deals with this. So, apart from finite and infinite degrees of freedom, we don't need any other case. What do we need? We don't need anything. Our problems are nicely explained by second quantized quantum field theory. For these few cases, very few cases which are not explained, we have string theory, again, which has still not been experimentally verified. But we do not need the third quantization. This is what I would like to tell you.